So, welcome back, everyone. Hope you had a refreshing break. For those who just joined us, I'm Perry Adeli, and I manage the Batteries program at the Nickel Institute. A reminder that Nickel Institute follows strict antitrust guidelines. My colleague Iseline will pop the disclaimer in the chat box. Please continue to submit your questions via the Q&A feature, and we'll address them after each presentation. So the next keynote speaker does not need an introduction, but for the formality, Professor Stanley Whittingham, the 2019 Nobel Prize winner in chemistry for his development of lithium-ion batteries. He's the Sani Distinguished Professor of Chemistry and Material Science and Engineering at Binghamton University. He is the director of the Northeast Center for Chemical Energy Storage, and he's also on the leadership team of the two U.S. battery consortia, New York Battery and Energy Storage Technology Consortium, and NatBat. It is my utmost pleasure to give the floor to the Professor Stan Whittingham.
Thank you very much. Can you hear me okay?
Yes, I can hear you well, and the presentation looks perfect.
Good, thank you very much. So I want to talk about some of the research we've been doing as part of the Battery 500 consortium. And this is a consortium that's trying to push the limits of lithium batteries, and half of its effort is aimed at high nickel NMC systems. So I want to discuss those and what we're doing so we can use more nickel in the batteries and less cobalt. So let me first thank the US Department of Energy, who's been supporting this work for the last close to 30 years. And I show you two examples of where nickel-based batteries are used, this large system in California, grid storage, and in the electric vehicles. So where do we stand at the present time in the Battery 500 consortium? The goal there is to get to 500 watt-hours per kilogram. I show you the data here for the first 5 years. So we're working this period with 60% nickel, 20% cobalt, 20% manganese. We're using a pure lithium metal anode and an ether-based electrolyte. And you can see how we're doing. This is data from my ex-student, Jay Xiao, who's at Pacific Northwest National Lab. She's leading the effort there. And I show you the typical pouch cell we're using for these tests. Pouch cells are made in Washington State and go to Idaho National Lab for testing. So all the actual energy density I show you here are real energy densities. The cell is weighed and the electrochemistry. So you can see over the 5-year period, from 2017, we've gone to less than 50 cycles at 300 watt-hours per kilogram, to in 2021, we're now at 600 cycles. And I'm told right now we're about 800 cycles with 622. I don't think I need to describe what these materials are, so I'll jump that bit. Right now, the baseline for the consortium is 80% nickel, 10% cobalt, 10% manganese. And the rationale for this whole consortium is that the present lithium batteries have a much lower energy density than they're theoretically capable of. So look at what's inside this oval I've shown you here. So the volumetric energy density in commercial cells, and these are mostly cylindrical cells, are from 11% to 25%. So a huge opportunity to increase that. On the weight basis, exactly the same thing, about 25%. So our goal is, in fact, to get this up to 50% and this up to 500. To do this, we obviously have to get rid of the graphite in the batteries. The graphite takes up half the volume, and for every 7 grams of lithium, we need 70 grams of graphite. So we have to go away from the graphite anode. We also need higher lithium content cathodes. So it means we have to go to a higher lithium content in the layered oxides. And I'll show you in a moment, this means basically going to higher nickel. Or we can use the phosphates, but there we need to put extra lithium in. But for all these, ideally, what we want are materials that have higher ionic and electronic conductivities. This will allow us to make thicker electrodes, which will reduce the amount of the current collector and separator. So if we look on the right-hand side here, this is work from South Korea. Shows the thermal stability of nickel compounds. You can see here's the most stable one, gives off oxygen about 320. This only has 1/3 of a nickel in it and only 160 milliampere hours per gram. If we want higher capacities, higher energy density, we have to go to higher nickel. This is 85%. But now the thermal stability, it drops by 100 degrees. No one is suggesting the batteries are going to go to these temperatures, but these temperatures are a direct measure of how reactive these materials are with the environment, either with the air or with the electrolytes. So we know, for example, 80% nickel reacts very readily with regular ambient air to form carbonates and hydroxides. It also reacts with most of the common electrolytes. So we have to stabilize this material. And it really doesn't matter how high you charge these materials. The thermal stability is directly related to the nickel content with a few other variations, but essentially it's the nickel content. So as you push the nickel content up, which is what we want to do to get higher energy density, we have to reduce the reactivity of these materials. So there are a number of options to do this. We can decrease the surface area, for example, going to single crystals. We can modify the material, both the surface, to reduce the reactivity. And it turns out this also reduces the first cycle loss, and I'll describe that in a moment. Or we can do bulk substitution, which reduce the mobility of the ions and the bulk of the material, which in turn reduce the oxygen evolution. And this will give us then a higher energy density. So let's just look at this single crystal issue. And I expect Jeff talked about that earlier today. If we go all the way back to day one in the 1970s, when we built the first lithium-ion batteries, we used titanium disulfide, very large single crystals. These were probably 100 microns thick and up to 1 centimeter in length. So very, very large. It reduced the reactivity with the environment, but also we could do that because TiS2 is essentially a metallic conductor. So we have no difficulty in getting electrons in and out. And that higher metallic conductivity also allows the lithium ions to move very fast. Sony, when they made lithium cobalt oxide batteries, also wanted to use very large particles. And this should say this is 20 micrometer particles. This particular picture is one of Jeff's, but the real Sony cells were about 4 or 5 times this size. But over time, people wanted higher and higher power densities, and we went to this meatball configuration where the large particles, probably about 5 to 10 microns across, and the primary particles are about 200 nanometers. So this increases the power density. There's been a push lately to go back to single crystals to reduce the reactivity, and Jeff has been a champion of this. So why go to single crystals? I've already mentioned less surface area, less side reactions, longer life, and as Jeff says, this in principle allows million-mile batteries. What it really does is allow your vehicles to be attached to the grid at all times when the vehicle is not actually moving. So it can act as grid storage, grid stabilization, and provide power to your house. The question is, the challenges here, Jay also showed that if you keep the size under 3 microns, they will not crack. So the big issue with the meatballs is they crack as you cycle them. The next question is, how can we easily make these in the tonnage quantities? So we need the chemists to go back and really look at how to make these materials. So let's just look at some of the other options. First, single crystal, 80% nickel, fairly easy to make. These particular single crystals were cycled under what we call our P&L protocol. This is using an ether-based electrolyte, C/10 charging, C/3 discharge, and you can see it's holding its capacity very well over 150 cycles, and it can go much further than that. The challenge of single crystals is it will not readily allow fast charging. So we'll have to have slow charging, but you'll have this option of fast charging, a longer life. So let's look at how do we get higher energy density, higher capacity out of these materials. It turns out all these layered materials show what we describe as a first cycle capacity loss. And this shows you a typical cycling curve here. We charge it up to about 4.4 volts, we discharge it, and then we're losing, in this case, about 30 milliampere hours per gram. This is typically 10 to 15% of the loss, and you do not get that back in subsequent cycles. So as an issue, can we reduce that loss? Because this is very important, because this is at a low potential, it's about 3.5 volts. So where the electrolyte and the cathode are the most stable. Get higher energy densities, we'd have to push the voltage higher, and we know the electrolyte is not stable. So we need to work out why that happens and how can we solve it. So we looked at measuring the diffusion coefficient in these materials, and the black circles here show you lithium going into the 80% nickel. And you can see the diffusion coefficient falls off a cliff after about 70, 75% occupancy. And this can be related to the diffusion mechanism, which is a divacancy mechanism. So you need 2 vacancies, and these fall off obviously very rapidly as you fill the lattice. And this can be compared with if you're giving a lecture in person, the lecture hall is 80% full. The only empty seats are single seats somewhere in the middle. So everybody has to move to allow somebody else to come in. Taking the lithium out, we do not have the same problem. So fast charging is much easier. It's only in the last little bit that we lose diffusion. So this is the same as after a lecture, everybody moves out of the lecture hall smoothly. So we want to check out that diffusion was really the issue. We still don't know whether it's diffusion in all the bulk of the material or in the surface layers. But if we look at what we typically might do, if we're charging these materials to different voltages, you'll see we got the first cycle loss in every case, whether it's 4.2 volts, 4.8 volts. You'll see with the standard carbonate electrolytes, there's a big spread at 4.8 volts between discharge and charge. We're getting surface reactions and resistive films on the surface. A little bit in the green one at 4.6 volts. So now look at how much capacity we get if we go to 45 degrees from room temperature. And this is 4.4 volts. You see much higher capacity. The first cycle loss is much reduced, clearly indicating diffusion. You see now at 4.6 volts, we're now getting spread of charge and discharge, showing we're getting reaction with the electrolyte. So as soon as you go higher in temperature, the electrolyte is becoming less stable. So we have to find ways of stabilizing this lattice. And the ways we opted to do it was to modify the surface and the bulk of it. And we chose to modify the surface by using niobium. And why we chose niobium, because lithium niobium oxides are known to be good ionic conductors. So this is essentially putting an electrolyte kind of surface on these materials to protect the surface. And depending on what temperature we use, depends on whether we get surface diffusion or bulk diffusion. But what we found out, if we get the meatballs, immerse them in the niobium oxide solution, and then 5 to 500 degrees centigrade, we get a complete coating on the outside, plus diffusion into the first few nanometers. As the niobium goes in, it kicks some of the manganese out. So this surface film is a complex lithium niobium manganese oxide phase, and this is protecting the surface. And if you look at this plot on the right, you can see as soon as you put a little bit of niobium in there, it doesn't matter whether it's 1% or 3%, it makes no difference. We're almost eliminating half of this first cycle loss. So modifying the surface can get us back this capacity. And what we think we can do is get it all back by doing the appropriate modification. But the other option is to actually heat it to higher temperatures. And in this case, if we heat to higher temperature, and what we did here was using the same lithium, niobium, ethoxides, soak the meatballs in it, and we get perfect solid solution in here, and no surface species to speak of until we get to very high niobium concentrations. The lattice just changed in size, so it's getting solid solutions. And you can see at 2%, we're getting a second phase, and maybe a little bit here, but nothing at the 1% or less. And the phase we are observing at higher niobium contents is the lithium-3 niobium 04. What we did in the end, and some of this, is we actually added the niobium with the lithium at the firing stage, rather than adding the niobium compounds to the meatballs. This eliminates one whole firing step and reduces the cost of making the material. So if we look at these materials, you can see we get, we've done 200 plus cycles on these. This is using carbonate-based electrolytes, standard cycling regime. And you can see the capacity of the niobium-free material falls the fastest. This is a black one here. The one with 0.7, we have some wetting issues here. It falls off less rapidly. But the challenge in these carbonate electrolytes is the capacity. You'll notice we put more niobium in, initial capacity is dropping. And this is just the same data plotted as a percentage. So you can see with 2% niobium in there, we see no capacity loss whatsoever. So niobium is really stabilizing these high nickel. And I should emphasize, in this case, we're now up to 90% nickel. So we've gone beyond the 80%. So we can stabilize 90% against reactions in the electrolyte. We now look at the effect as we cycle these materials. The one at the top here is no niobium. You can see now the capacity fade up here to 0.7 niobium, much less capacity fade. By the time we get to 2% niobium, even 1.4, you can see we got no capacity fade at all, no voltage fade. So a little bit of niobium is working wonders with these materials. If we now look at the capacity change with voltage, you can see exactly the same essential behavior. We look at this no niobium, you can see these peaks are shifting the whole time, telling us we're changing the composition of the material. As soon as we get to higher niobium, even 0.7, we're not seeing any shifts of this peak. So the redox behavior is constant once you put a little bit of niobium into the lattice. Similarly, if we look at the impedance of these cells, this is after 50 cycles, no niobium, little bit of niobium. You can see a difference here. After 100 cycles, 150, 200 cycles, again, niobium is preventing the formation of these resistive materials on the surface of this high nickel material. So this is, again, indication we can use high nickel materials. So key thing we found out, why does this work? What we found out is putting the niobium into the material It stabilizes the lattice. And you can see in this image down here, no nickel, sorry, no niobium, large cracking of the meatballs, a little bit of niobium, they're all minor cracks in here. So we're not getting extra reaction of the electrolyte with the surface of the materials. And this again is in a carbonate-based electrolyte. And you can see these are 3 different cells, very stable over 200 cycles, essentially no capacity loss. But I say this is again with the carbonate electrolytes. What we've been doing is switching away from those because carbonates are not good for lithium electrode deposition. Here's now showing similar data, but in this case, we've now switched away from the carbonates to the ether-based electrolytes, following the PNL protocol. And you can see we're now getting quite a bit higher capacity, over 200 compared with 180, and there's very little capacity loss. So we're getting essentially 100% Coulombic efficiency at realistic loadings. So I'd advise all of you watching here, when you read a paper in literature, you see what loadings they're using in milligrams per square centimeter. A lot of people will be using very low loadings, 1 to 2, which are meaningless, also using a large amount of electrolyte. We use here the minimum amount of electrolyte we can get these cells to cycle with, which is what you need in a practical device. So what we have shown here is that high nickel materials can be used. We can basically eliminate their reactivity, both with the environment. So these materials are more stable if you keep them in the lab than the pure, say, 80–90% material. We found that niobium is particularly effective. We haven't looked at all other materials, but most commercial NMCs are stabilized with one element or another. Typically, most common one is boron. Others are using aluminum, but we found niobium is most effective. It can form coatings readily on these NMCs. It's a complex composition. It reduces the first cycle loss. And we've shown that niobium can be substituted into the NMC lattice. If we go to too high a temperature, it will get pushed out of the lattice onto the surface. So it can clearly enhance the capacity retention on extended cycling. But what we need now for all these NMC materials are cost-effective manufacturing technologies. These are still made by batch processes. Now, hundreds of tons a year, all batch processes. We need to find a continuous lower cost process, and we're going to have to put coating materials and substitutions in them, particularly as we go to higher and higher nickel contents. And I will stop there and try to answer any questions you might have. Thank you very much.
Many thanks for the presentation and the amazing insights that you provided for us. Again, it's quite an honor to have you with us today. We do have questions. I'll start. So why do we have around 15% loss at half cell? Is it because of a structure change?
It doesn't matter whether it's half cell or full cell. It's totally a diffusion issue. You can't get the last 10 or 15% to go in at a reasonable rate. And it doesn't matter whether you fully charge the cell. If we only take 20% of the lithium out, we let it relax, we'll get almost none to go back in again. So it's that filling those last 10 or 15% of the lithium sites is the difficulty.
Thanks. Another question. What does the results you presented mean for the future of NMC electrodes in EV applications?
I think the big push in EV applications today is to get the cobalt out. The more cobalt we get out, the more nickel we need to put in. And all indications are we can certainly go to 80% nickel. We can probably go higher. The question will be can we make pouch cells with those high nickel levels, or will we have to go to cylindrical or prismatic cells where you have a hard case that can contain any gas that might be given off? But substituting with materials like niobium may also eliminate the gas evolution.
One last question. Is it niobium coating or niobium doping that can prevent the degradation of NMC cathode at high rate?
Both. So we hope we coat to stabilize the surface, but we need some niobium inside the lattice to stop the manganese, nickel, and cobalt from moving. If they can't move, then the oxygen cannot be evolved. So we need it both within the lattice and we need it on the surface.
Thank you very much. I really appreciate your time, and we'll inform you of the remaining questions later.
Okay, thank you.
Thank you.